You select for evolvability.
Hello? Is that mic picking me up? I probably don't need it, right? Can you hear me? Okay, cool. Okay. I'm going to talk about optimal selection for evolvability. As many of you will know, there are lots of definitions of evolvability around. I'm going to be using this by Hansen. Evolvability is the ability of the genetic system to produce and maintain potentially adaptive genetic variants. So it's evolvability is a propensity. It's to do with the production of the right kind of variants in a population. It's very similar to Altenberg's definition and many others. Where does evolvability come from? Well, partially, it comes from the mapping from genome to phenome. So if you occupy, so on the left-hand side here, I have a representation of a space of genomes. If you occupy somewhere there, which you do, then when a mutation event happens, you have a probability distribution over the genomes that you could reach. Then the mapping from genome to phenome gives you a probability distribution over the phenomes that you could reach. So this is a space of organisms, or in evolutionary computation, a space of solutions. And then the environment gives us a mapping from phenome to fitness. And the result is, when a mutation happens, we have a probability distribution over the fitness after the event. Evolvability is often defined or quantified in terms of this distribution of fitness effects of a mutation. So this axis is the relative fitness effects of a mutation, 1 meaning neutral, nothing happened, 0 meaning lethal, you're dead. This is just an example probability distribution where most mutations are lethal and there's a bump around neutrality. So one proposed measure of evolvability is just the probability of a beneficial mutation, so this area here, and another proposed measure is the variance or standard deviation of this bump. Now, since evolvability is usually defined in terms, or often defined in terms of this distribution of fitness effects, and this distribution partially comes from the mapping from genome to phenome, and the mapping from genome to phenome is partially determined by the organism itself or the organism's parent, then the observation is that evolvability is heritable and evolvability can evolve. Which leads to many questions, but my question is, how much should we select for evolvability? So this isn't trying to understand what happens in nature. This is, if we have an artificial population and we can see or we can estimate the evolvability of the individuals in the population, shouldn't we select for it? And if so, how much? Because there's going to be a trade-off between selecting for evolvability and fitness or adaptedness itself. So to study this question, I looked at a very simple model where I've abstracted away the fitness function. There's no fitness function. I've abstracted away the mapping from genome to phenome, and we end up with a situation where each individual in the population is just consists of two numbers, an A number and a B number. The A number is going to represent adaptedness or fitness or whatever you want to call it, and the B number is going to represent evolvability. So these are just numbers, and what happens during a mutation? Well, we're going to just add Gaussian noise to each of them. So the A number after a mutation is the A number before the mutation plus a number taken from a normal distribution, 0 mean, where the standard deviation of that is determined by the B number. Okay, so we've taken one of the proposed measures of evolvability, which is the standard deviation of the distribution of fitness effects, and we're using it as the definition of evolvability in this model. The B number also undergoes mutation, so we take the B number from before the mutation and we add a number taken from a normal distribution, this time with a fixed standard deviation beta, which is a parameter of the model. Selection is done by ranking and truncation. So we rank the individuals by this value, gamma A plus 1 minus gamma B, and we take individuals from the top, and they become the parents of the next generation. So gamma is a trade-off parameter in how strongly we're selecting for A, adaptedness, or B, evolvability, taking values between 0 and 1. Just to illustrate, if gamma is 1, when we rank by this value, by this quantity, we're just ranking the population by their A values, and when we take from the top, we're selecting for A. Conversely, if gamma is 0, we're just selecting for B, evolvability. In order to... so I make this model even simpler to make it easier to study and to analyze. So now we have a population size of 2. And we're going to take here, just for this example, gamma equals 1/2. So we have 2 individuals. Each has an A value and a B value. We look at the quantities, gamma A plus 1 minus gamma B. This one has the maximum value, so it becomes the parent of the next generation. We duplicate that individual. It has 2 offspring. We add some noise to each of the A and B values, and repeat. And then because we only have 1 parent in each generation, we're going to call the A value of the parent in the teeth generation A of T, right? So A of 1 is 3, B of 1 is 1, A of 2 is 3.2, and so on. Back to the question, what's the optimal trade-off parameter? How much should we select for evolvability? Or specifically, what we're really asking in this model is, what's the value of gamma that maximizes at some particular time in the future, t end, which is now a new parameter, what's the value of gamma that maximizes the expected value of the A by that time? And you see that there's a trade-off, because if we set gamma to 0 and we only select for B, then the standard deviation of the A mutations becomes very large, but we never select for A, so you just get a random walk in A. So the expected value of A at any time is 0. So the answer definitely isn't just select for evolvability. Okay, so what happens to the A and B values from one time step to the next? So that's what this slide is about. So first, our parent has these values A and B. It has 2 offspring, each with its own values of A and B. Where do they come from? Well, the A value of an offspring is just the A value of the parent plus, this is a random variable with a normal distribution with 0 mean. The other offspring has the same thing, but of course this is a different instance. This is a different random variable with the same distribution, right? And similar situation for the B values. Then the surviving offspring is the one that has the A and B values that give the maximum value of this quantity, gamma A plus 1 minus gamma B, the thing we're ranking by. So the notation is rather messy, but in the next generation, so the relationship between the values in the next generation compared to the current is this. The A and B pair in the next generation is the pair from this generation's offspring that maximizes this quantity. And because these A1, A2, B1, and B2 only differ from each other in these 4 random variables, as in these are equal, right? These A's are equal, these B's are equal. What we're doing is taking the AB pair where the corresponding mutations maximize this quantity. So to be clear, we generate 2 A mutations, 2 B mutations, we pair them up. The one that has the maximum value of this quantity, we take those mutations, essentially apply them to the parent of the last generation to get the parent of the next. That's one way you can think of it. Now this starts looking like something we can analyze, because all of these are normally distributed random variables, which are nice to work with, and taking the maximum. So this is a kind of quirky but straightforward problem in order statistics. So let's look at a simpler problem in order statistics. So this here is the problem of, given two random variables, so we have two random variables, and we're going to throw away the one with the smallest value, keep the one with the largest value, and ask, what's the expected value of the thing we're left with, right? Let's see. As an illustrative example, let's say we roll 2 dice, and we keep the one with the largest value. And then you can ask, what's the expected value of the number I'm left with? To avoid confusion, we're not asking the expected value of the distribution from which that number was drawn. That's different. To see that, imagine you roll 100 dice, you take the one with the largest value. The expected value of that thing is going to be very close to 6, right? Not 3.5. And you calculate that like this. So phi1 is the probability distribution function, the PDF of one of our variables. Phi2 is the PDF of the other variable, and the capital phi's are the corresponding cumulative density functions. So what does this thing on the left-hand side say? Well, this is the probability, it's a density, but let's pretend. This is the probability of getting a particular value of x for a particular value for our first variable. This is the probability that the other variable takes a value less than that. So the product is the probability that our first variable takes that value and the second variable is less. In other words, that's the probability that this particular x is the maximum value you saw, conditional on the first variable being the one that had the maximum value. Multiply by the value and integrate to get the expected value. And that's not the whole story, because it might be the case that the second variable had the larger value. If that's the case, this tells us the expected value, well, when we sum them, it tells us the expected value of the maximum. Don't worry if you don't fully understand what's going on, just try to get an intuitive idea. Right, so this is similar to the problem we have, but it's much simpler. Yes. If the two variables actually have the same probability distribution, that, of course, simplifies to this thing, which it turns out evaluates to this, which is a nice result. It says if you have if you take two numbers from a zero mean normal distribution and you throw away the smallest one, the number you're left with is the standard deviation of that distribution over root pi. So that's nice. Recap what we're actually trying to do. Remember, the A and B values, we're trying to determine the relationship between the A and B values in one generation and the next. So the A and B values in the next generation, how do we get them? We get them by adding the pair of mutations that maximize this sum. So this is different. We have 4 random variables. We have 2 A mutations, 2 B mutations, and we want the pair. Essentially, we want the expected value of the pair that have the maximum of this quantity. Okay, stepping towards that, let's set gamma to a half. So now we're asking for the expected value of the pair that just have the maximum sum. Ignore gamma. We have 2 pairs of numbers. What are the expected values of the components that have the maximum sum? Definitely don't worry if you don't understand this one. This is just to illustrate how I got to the result. This product is the probability of getting a particular pair of values for the first pair of random the first AB pair, right? This is the probability that the other pair, that the sum of the other pair is less than the sum of the first pair. So together, it's the probability that we got these particular values, and by the way, the sum is bigger than the other pair. For the same reason as before, multiply by 2, because it might be the case that the second pair of mutations had a larger sum than the first. And this integral evaluates to this thing, which is again nice, but it's a nonlinear function of the standard deviations of the mutations, and it's a bit messier. Now, we can use the result from the previous slide, but I'm not going to show you how, to get the expected value of the A and B and just to recap, A is adaptedness, B is evolvability, or that's what it's supposed to represent. So we've got here the expected values of each of these in the next generation in terms of their values in this generation. And what happens, the expected value of the B is what it was before, plus the standard deviation of the mutation we applied to it, multiplied by this factor, this function of 1 minus gamma. The A value, again, that thing increases in expectation by B, the current previous B value multiplied by the same function of gamma. So this thing is giving us a trade-off between the rate at which we expect A to increase and the rate at which we expect B to increase in units of the mutational standard deviations that we're applying. Now we have a recurrence relation because we know what B is in terms of the previous B, and we know what A is in terms of the previous A and B, and we can solve this recurrence relation to give something that isn't very nice, but we have it, right? So this, you have to be careful about what you're taking the expectation over, because now we're taking the expectation over every mutation event that's happened so far, but now we have the expected value of A, the adaptedness or fitness, by time t, and it's this expression, which we can now maximize with respect to gamma. So find the gamma that maximizes this, take the derivative with respect to gamma, say equals 0, solve for gamma, make sure you have a maximum. Bam, done. Right. This is the optimal value of that trade-off parameter I talked about earlier in a surprisingly compact form where I've introduced this dummy variable. And this variable is just a fairly simple function of 3 parameters. Beta is remember, the standard deviation of the mutations affecting evolvability, affecting B. T end is the particular time in the future at which we want to increase for A to be as large as possible, and B naught is the initial B value. So you see the optimal amount to select for evolvability is just determined by this particular combination of these 3 parameters, which is nice. Here's a plot of the optimal value of gamma as a function of, I've taken the reciprocal, so now it's the optimal value of gamma as a function of B naught, initial evolvability, over beta T end minus 1. I should have changed the initial conditions so that this was just T end, but... so what are the features of this? If your initial evolvability is very large, then the optimal value of gamma tends asymptotically towards 1. What does that say? If your evolvability is already large, don't bother selecting for evolvability. Conversely, if the denominator is large, so beta times T end is something like the amount you expect evolvability to increase in the time given if you select for it. Right? So if it's possible to increase evolvability through selection, then you can't see it here. You would see it in the reciprocal graph, but the optimal value of gamma tends asymptotically to half as the denominator goes to infinity. What else is interesting about this? Yes, it never pays off to... so you notice gamma is never less than a half. What does that say? It says never select for evolvability more than you select for adaptedness itself, which I think is the most interesting result, but maybe it's very obvious. I don't know. Here's some empirical verification. I simulated this process, tried lots of values of gamma over many, many trials, because with a population size of 2, this was very, very noisy. And it verifies the result. If you're sharp-eyed, you'll see that something weird's going on down here that I might talk about in questions if anyone's interested. But it kind of verifies the result. So the optimal value of gamma was found to be very close to the analytic result. Okay. So obviously, the applicability of this result depends on the extent to which the model actually models anything. The model is extremely simple and with some very restrictive simplifications. So there's no fitness function, there's no mapping from genome to phenome, and A and B, that's adaptedness and evolvability, they're just numbers. They can increase without end, and that's kind of strange. But I found this model rather illustrative, especially by modifying this model, adding features to it, like evolvability, decay, and things like that. Certain features of the result are fairly robust. For example, in every variant of the model I've tried, it never pays off to select for evolvability more than adaptedness. Again, that might be something that's obvious, but I found it interesting. And I hope that I'm presenting this here in the hope that other people find this model illustrative and it can be the start of a conversation. Thank you very much. That's the end of my talk.